Welcome to all. I am Mahalakshmi, Assistant Professor in Department of Physics, St. Joseph College for Women, Tripur. Now we are going to discuss about Gauss'S law and its applications. Gauss's law definition: the total electric flux through a closed surface is equal to 1 by epsilon naught times the magnitude of the charge enclosed by it is y equal to closed surface En ds equal to q by epsilon naught. Here, epsilon is the absolute permittivity of free phase, and epsilon naught values epsilon naught equal to 8.854 in 10 power minus 12 Faraday per meter. Q is the total charge enclosed. The next, applications of Gauss law. Gauss law can be used to solve complex electrostatic problems involving unique symmetries like cylindrical, spherical, or planar symmetry. The next, content. Electric field due to infinite wire, electric field due to infinite plate sheet, electric field due thin spherical cell. Then first one electric field outside the spherical cell, then second one electric field inside the spherical cell. The next, electric field due to infinite wire. Consider an infinitely long wire with a linear charge density lambda and length L. To calculate electric field, we assume a cylindrical Gaussian surface due to the symmetry of wire, as the electric field E is radial in direction. Flux through the end of the cylindrical surface will be 0, as electric field and area vector are perpendicular to each other. The only flowing electric flux will be through the curved Gaussian surface. The electric field is perpendicular to every point of the curved surface. Its magnitude will be constant. The next, image 1, we consider a cylindrical Gaussian surface of radius r and length L. The surface area of the curved cylindrical surface will be 2 pi rl. The electric flux through the curve will be electrostatics E into 2 pi rl, and according to Gauss law, pi equal to q divided by epsilon naught. E into 2 pi rl equal to lambda L divided by epsilon naught. The term L cancelled. This equation C equal to lambda divided by 2 pi epsilon naught r. Vectorically, the above relation says E vector equal to lambda divided by 2 pi epsilon naught r into n cap, where n cap is the radial unit vector pointing the direction of electric field E vector. The next, image 2, direction of electric field is radially outward in case of positive linear charge density. Note 1, direction of the electric field will be radially outward. A linear charge density is positive and will be radially inward in linear charge density is negative. Note 2, we consider only the enclosed charge inside the Gaussian surface. Note 3, the assumption that the wire is infinitely long important because without this assumption, the electric field will not be perpendicular to the curved cylindrical Gaussian surface and will at some angle with the surface. The next, electric field due to infinite plate sheet. Imagine an infinite plate sheet with surface charge density sigma and a cross section area A. The position of the infinite plane sheet is given in the figure below. Image 3, infinite charge state. The direction of the electric field due to infinite charge state will be perpendicular to the plane of the sheet. Let's consider a cylindrical Gaussian surface. The axis is normal to plane of the sheet. The electric field can be evaluated from Gauss's law as, according to Gauss's law, pi equal to q divided by epsilon naught. The next, from continuous charge distribution charge, q will be sigma a. We will consider electric flux only from the two ends of the assumed Gaussian surface. This is because the curved surface area and an electric field are normal to each other, thereby producing zero electric flux. So the net electric flux will be pi equal to EA minus into minus EA minus minus equal minus minus plus pi equal to 2EA. Then we can write pi value substituting this 2EA equal to sigma A divided by epsilon naught. The next, the term A cancel out, which means electric field due to infinite plane sheet is independent of cross section area A and equals to E equal to sigma divided by 2 epsilon naught. In vector form, the above equations can be written as E vector equal to lambda divided by 2 pi epsilon naught r into n cap, whereas n cap unit vector visiting direction of electric field perpendicular and away from the infinite sheet. Note 1. The direction of electric field is away from the infinite sheet if the surface charge density is positive and towards the infinite sheet if the surface charge density is negative. Note 2. Electric field due to the infinite sheet is independent of this position. The next, electric field due thin spherical cell. Consider a thin spherical cell of surface charge density sigma and a radius r. By observation, it's obvious that cell has spherical symmetry. The electric field due to the spherical cell can be evaluated in the two different positions. Then first one, electric field outside the spherical cell. Then second one, electric field inside the spherical cell. The next, electric field outside the spherical cell. Image 4, diagram of spherical cell with the point P outside. Let us find out the electric field intensity at a point P outside the spherical cell such that OP equal to R. Here we take Gaussian surface as a sphere of radius R. The electric field intensity E vector is same at every point of Gaussian surface directed radially outwards as is unit vector n cap, so that theta is equal to 0 degree. The next, according to Gauss's law, E closed surface ds equal to q by epsilon naught. A into 4 by r squared equal to q divided by epsilon naught. E equal to q divided by 4 by r squared epsilon naught. Hence, it is clear that electric intensity at any point outside the spherical cell is such as if the entire charge is concentrated at the center of the cell. Field at the surface of the cell, for this we have R equal to R. Therefore, E equal to Q divided by 4 by R square epsilon naught. If sigma coulomb per meter is the charge density on the cell, then Q equal to 4 by R square into sigma. Therefore, E equal to Q swell substituting this 4 by R square into sigma divided by 4 by R square epsilon naught equal to 4 by R square 4 by cancel equal to sigma divided by epsilon naught. The next, electric field inside the spherical cell. Image 5, diagram of spherical cell with the point P inside. If the point P lies inside the spherical cell, then Gaussian surface is a surface sphere of radius r. The next, as there is no charge inside the spherical cell, Gaussian surface encloses no charge. That is q is equal to 0. Hence the field inside the spherical shell is always 0. Therefore, A is equal to 0. Hence the field inside the spherical shell is always 0. Note, there is no electric field inside the spherical shell because of absence of enclosed charge. Thank you for listening.